I prepared some French stuff. Je m'appelle Arnon, je suis de l'Université de Tel Aviv, en Israël. Vous pouvez voir notre beau campus derrière moi. Je suis très heureux d'être ici. C'est un grand honneur et merci de m'avoir invité. Malheureusement, je ne peux pas parler en français, donc je vais maintenant passer à l'anglais. I will share my screen in just a second. All right, here it is. So, can you see it all?
Perfectly, yes.
Great. All right, so in this talk, I would like to present you with the concept of personalization in education. We will discuss whether algorithms can act better than humans. I was told by the organizers that I should prepare for an audience that is not necessarily familiar with the required background to my talk. So I prepared my talk accordingly. I hope it's going to interest you all. In any case, it will give us a shared ground for this discussion. I have been studying the issue of algorithm-based personalization in the context of mathematics education, but you could definitely think of it in many other educational contexts as well. I would like to thank upfront my colleagues, Professor Michal Tabach and Dr. Anat Cohen, my colleagues in Tel Aviv University, and Professor Kobi Gal, my colleague from Ben Gurion University, all in Israel. Also, I would like to thank our wonderful research team of students and researchers that were part of this. We were all part of a large project funded by the Israeli Ministry of Education, which overall aimed at promoting technology integration in mathematics education. So let's start with a quick time travel. Let's go back to the 80s. How wonderful was it back then, right? The hairstyles, the dance movements, the sophisticated animation, and most relevant to our discussion, the realization that schools faced a big problem. Students were normal. More precisely, students' achievements were normally distributed. And to put it simply, if we took a classroom of 30 students, about 20 of them would achieve a somewhat average score, and there would be about 5 extremely high achievers and 5 extremely low achievers. And this is the pattern we see here in the very famous graph. So we find normal distribution everywhere. For example, if we count how many times people in a given country visit a patisserie per week, we would get a normal distribution, right? The majority of the people would visit 2 or 3 times a week, and then there's a small group who would visit on a daily basis, and a small group who would rarely visit. And this picture is, of course, very different in France. Statistics show us that the majority of the people visit patisseries regularly. So why do I talk about patisseries? What does it have to do with education? We all hope that students' achievements would demonstrate a pattern more similar to the frequency of patisserie visits in France than to the frequency of patisserie visits in any other country. So we would want that students would achieve high scores. Most of the students would achieve high scores. So back in the 80s, Benjamin Bloom, the American educational psychologist, showed that this was indeed possible. Let us recall very shortly what Bloom did, because it's very relevant to our algorithm. Bloom demonstrated how to achieve this desirable goal. Instead of merely lecturing to students, he advised teachers to provide students with useful feedback from which the students could learn and improve and achieve mastery. This was the code word, mastery. And it worked. Students' achievements increased and the variance in scores decreased, which is good. So this is the red graph. But Bloom took it another step forward. He advised teachers to personally tutor each student, to identify their difficulties, to support their progress individually. And this also worked like a magic. Student scores increased dramatically with only little variance. And this is the famous cyan graph. So this meant that everybody performed almost perfectly. Now, Bloom's ideas had quickly spread, but there was a problem. When schools wished to implement his ideas, there wasn't enough manpower and not enough time to tutor every student on a one-on-one basis. So also back in the 80s, at about the same time of Bloom's ideas, computers have come around as a personal aid. And this at first gave Bloom's ideas a boost. If teachers can't dedicate as much time as needed to each student, computers will. And indeed today, after a few decades of research and development in this direction, we know that computers can, in principle, help students achieve mastery in ways that mimic personal tutoring as Bloom envisioned it. And based on this vast experience, emerged the popularity of implementing computer-based personalization in education, which is the focus of my talk. However, we also know today that although computers are here to stay, so are teachers. Teachers serve as crucial educational agents, and classroom and schools serve as very important social structures. And of course, teachers work closely with computers for the benefit of the students. And teachers these days wish to enrich their students with the many resources available on the internet. They wish they could use these resources to give each student their own personalized path of learning. And this causes kind of a new problem. There are too many choices for teachers. So if you are a math teacher who searches online for activities to your students, you could easily find hundreds of relevant websites, and many of them will offer you with hundreds of options. Sorting out what will best fit each of your students becomes a huge, huge burden. So it's like finding something to watch on Netflix, but not just for your own sake, but for each of your students. And this dream of too many possibilities can easily become a nightmare. And the problem gets even worse because you realize that one activity will not suffice. So it's better to tailor each student with a set of activities. And even worse, you should order these activities in an increasing order of difficulty, because the students should move forward slowly and they should be kept challenged. And this is exactly where our novel algorithm gets into the picture. So the algorithm that we have developed takes a large repository of educational resources and fits for each student a personalized sequence of resources that will best promote their learning. And not only that the sequence itself is personalized, it is ordered in an increased level of difficulty, which is also personalized. This is done based on past experience of other students' engagement with these resources and of finding to which of those past students each current student is most similar, which again reminds the way that Netflix and Amazon and many other web services today work when they recommend products or movies to users. This is called collaborative filtering. It's tailoring something to you based on the experience of other people who are similar to you. Our algorithm uses an advanced neural network, which is a computer software that mimics the way the human brain finds optimal solutions to complicated problems. In very simple terms, the neural network consists of many individual parts, each of which is responsible on solving a small part of the problem. And together they find the best solution to the original problem. So for proving that such an algorithm does good, that is, effectively promotes students, we have to empirically test it. And this usually includes a three-part process. First, we have to train the algorithm. We use a large data set in the order of tens of thousands of students for training the algorithm, that is to teach the algorithm what works for whom. For doing that, we use historical data that was already collected. Then we collect new data in active, authentic classrooms at the order of about a few tens of students at least, who all work on the same stuff. The purpose of this stage is to gather information to extract their baseline, the student's baseline, to feed the algorithm with the student's information, and to have it produced personalized recommendations. And finally, in the last stage, we take these recommendations back to the students and test for how it works. We test for their knowledge while and after working on that sequence. Now, if we want to test whether that algorithm is superior to human judgment, we have to run a similar process with another human-based type of recommendations, and then compare between students' achievements in both scenarios. Now, despite the fact that numerous methods for computerized personalization in education have been developed, such studies that compare between human and algorithm-based recommendations are still rare. We did it in the context of mathematics education, as I mentioned, specifically for elementary school. And we used a large commercial repository of mathematical applets. Small software component which aims at learning or practicing a very specific content-related concept. Applets are usually rich in graphics and require the learner to be active on some level. Applets have become very popular in recent years in mathematics and science education, and you can find dozens and hundreds of repositories of applets for various topics. So for example, the applet on the left, this one with this little nice dog, discusses the concept of number line with 2-digit numbers. So it's a very specific subtopic. It presents the student with a number line, which they could move further to the right or to the left. And they are asked to drag the labels with numbers to the right place on that number line. So the student is active during this task. The applet on the right is about simple fractions. It presents the student with pizzas, in each of which the student is asked to add toppings on a given portion of the dish. Here on 2/3 of the dish, on half of the dish, or on 1/3 of the dish. And the student clicks on the topping and spreads it over the pizzas. These applets give the students with an immediate feedback, and the students can rerun the task even if they got the answer right. Some of the applets requires open search, and some of them are more closed. So a single applet would usually require only a few minutes to complete. However, a single topic in mathematics may be covered by multiple applets. They could be different by their level of difficulty or by their usage scenarios. So the number of applets to cover a one-year mathematics curriculum may accumulate to dozens, maybe even hundreds. And that makes it quite difficult for the teacher to find the most effective sequence for each student. In the first study we conducted, we tested whether the algorithm was better than an expert teacher in this type of personalization, of personalizing sequences of tasks for students. We did so with about 80 4th and 5th grade students. The teacher we worked with was an expert on 3 important levels. First, she was expert in teaching mathematics for these grade levels. Secondly, she was expert in teaching mathematics using technology. And third, she was expert in using this specific platform. So she definitely knew what she was doing. First, all students took a predefined set of applets, and then they were randomly assigned into 2 subgroups. One was assigned with teacher-based recommendations, and the other with algorithm-based recommendations. So after the first stage, we extracted data from the system log files about how the students were engaging with the applet in terms of both achievements and time taken to complete the task. For the algorithm group, this information was fed as is into the algorithm. For the teacher group, the information was somehow summarized and organized and presented to the teacher. Now, you will not be surprised to hear that the teacher find it quite difficult to digest all the information that she was presented with and to act upon it on a personal basis. Therefore, she decided to divide the students in her group into 3 subgroups based on their overall level of understanding and similarity as she interpreted the data. And then she gave a different sequence of applets for each of the 3 groups. So she decided not to have personalized recommendations, but rather recommendation of 3 types. So what did we find? Let's compare the achievements in both groups. Recall that we talk about personalized recommendations. So we don't necessarily have students work on the same applets because each got personalized recommendations. So instead, we refer to the order of the applet in the sequence. So we will talk about the first applet, the second applet, the third applet. But for different students, this first and second and third, etc., may be different. So for the fifth graders, we clearly see that in most cases, students in the teacher group, this is the orange line. Can you see my mouse moving here? Yes, okay. So for the fifth graders, in most cases, the orange line is higher than the cyan line. The orange line is the teacher students, sorry, and the cyan line is the algorithm students. So in most cases, teacher won. For the fourth graders, there is no clear winner. In some cases, the cyan line demonstrates higher achievements, and in some cases, the orange line demonstrates that the teacher group got higher scores. What we have learned from this experiment was twofold. First, there are things that teachers know and algorithms don't. And when we interviewed the teacher and when we studied the algorithm recommendations in details, we learned that mostly what the teacher knew and the algorithm didn't was about complex relationships between different parts of content along the curriculum. So the teacher based her recommendations on her vast experience, and she knew how to promote students who found a given sub-content difficult. However, we also learned that there are things that algorithms know and the teachers don't. And mostly it was about how difficult a given applet is de facto. Apparently, the algorithm, of course, takes into consideration vast amount of historical data of many students. And from that, we learned that graphical user interface plays a very important role in the way students engage with computer-based educational content. And sometimes it takes them time to complete a task, not because it is more difficult for them, but because the graphical user interface is not that optimal. So following these insights, we designed a second study with a different group of students, this time 135 fourth and sixth graders. And again, in the first stage, all students took an identical predefined set of applets that served as a baseline. And then we randomly assigned them into two groups. One group got recommendations by our fancy algorithm, but this time the other group got an identical set of recommendations prepared by a few experts in mathematics education and in educational technology. And there was an important twist in this experiment. Eventually, at the last stage of the experiment, all students got a final set of identical applets that served as a post-test. The experts knew what these applets were, and the algorithm didn't know that. So the experts worked very hard. It took them a nice amount of a few hours to construct a single sequence that would potentially prepare students to the final task. They considered everything: content, level of difficulty, graphical user interface, time needed to complete the task. And all students in the experts group got this sequence. The students in the algorithm group got each a personalized sequence of applets. our main finding in this experiment seemed at first boring, I must admit, maybe even disappointing, because we found that both groups achieved similar scores in the post-test. So we were first wondering, how come the algorithm didn't beat the experts? How come the students in the algorithm group didn't achieve higher scores?
Arnon, just so that you know, you've reached 25 minutes. A little bit.
Oh, really? Okay, so I'll make it quick. But then we realized that this finding, all students getting the same scores, is actually fascinating and maybe even revolutionary. Because remember that the algorithm didn't know what the final tasks were. So without knowing that, the algorithm prepared the students to a task in the same manner that the experts did. But it did it with much less effort than the experts. So I think the final verdict in the question of whether the algorithm or the human teacher or experts should be in charge of leading personalized recommendations is not single-sided. It's not a question of either or. They should both work together. And furthermore, we learned that each side could benefit the other. Algorithms could benefit from teachers' knowledge, and teachers could benefit from algorithm knowledge. And if we have algorithms and teachers promoting each other, I think all of the educational milieu will benefit. And that's it. I think, sorry, I missed the 25-minute line.
No problem. Thank you very much for this presentation, which is open to discussion. Are there any questions? I don't have any on the chat here, but maybe a question for you. I did not fully understand how this works, but I imagine that the combinatorial explosion is huge. The number of possible orders of these applets is enormous. So don't you need an enormous number of data in order to decide in which order they should be placed?
So of course we do, in order to have the algorithm supply us with good recommendations. We had data in the order of tens of thousands of students with a few millions of data points. So each student in the historical data had worked on many applets, and each applet is logged with many rows. So we had the magnitude of a few millions of data rows. The algorithm works for a few hours, just to have some sense of it. But since it's implementing a neural network, it's not really like a linear code that would require an extremely exponential time to work. I can't hear you.
Sorry, thank you. Is there any other question?
Yes, I have one.
Very brief one, so that we have time.
Well, I wanted to know whether this way of teaching can be generalized to other fields beyond mathematics.
In principle, yes. You just have to recall that the algorithm should take into consideration relevant historical data. So it's not necessarily a good idea to take the very same algorithm that was trained on mathematics and to have it implemented on science or on history or on biology. I would say that this is a question that should be tested empirically, but I would guess that it will not work appropriately.
Thank you.
Thank you very much, Arnon. I think it's a very interesting idea that there might be a catalog of apps, maybe also a catalog of interesting problems, and that algorithm similar to Netflix would one day recommend to children or to teachers, you might like this next problem, or you might like this next app because this is for you, this is ready for you. So thank you very much for this idea.